Periodic waves have regular repetitions that can be described using a period and a frequency. So a typical example is a sound wave that's generated by the oscillation of the diaphragm of a speaker. So if we measure the pressure in this air medium at different points at a particular time t, then we see that part of the air is compressed and part of the air expands. So these are the compression and rarefaction regions. So this repeated compression and rarefaction results in the sound wave propagating from the speaker to another point in the medium without transferring any particle to that point. So this graph represents the pressure versus the distance from the speaker at a specific time t. So this is a snapshot of the medium at a particular time. So we have a compression region followed by rarefaction, back to compression, and so on along the x direction. Now on the other hand, if we monitor the pressure at a specific point in the medium, so at time t equals 0, the air is in compression, and after some time t, the air expands, and then it gets compressed, and then it expands. And this continues on as the wave propagates through this point. So using this plot over here, the period is the time taken for one oscillation of the wave to complete. So for example, if we start from this point, we have the maximum compression of the air, followed by the maximum expansion, and back to maximum compression. So that's one cycle of oscillation, being equal to the period. So note that this plot is the pressure versus time. And the frequency is the rate at which the wave repeats. So the period is the reciprocal of the frequency. And we'll look at some numbers to make sense of this. Now the amplitude is the magnitude of the maximum increase in pressure or decrease in pressure from the equilibrium pressure. So we may take our reference pressure initially as the atmospheric pressure for the air medium. And the energy of a wave increases with an increasing frequency. So we saw this from the energy equation for a traveling wave on a string. And the higher the frequency of the sound, the higher the pitch. So it'll sound something like this. Whereas a low frequency sounds something like this. Now if we use this plot instead of the pressure versus the distance from the source of the sound, the distance between successive corresponding positions, such as the peaks or troughs on a wave, is the wavelength. So for example, here we have peak to peak. So this is one way we can visualize the wavelength. Now a sinusoidal wave can be described by similar equations to a harmonic oscillator. So for example, we may measure the displacement from equilibrium or the pressure at a specific location in the medium as a function of time, and that could be represented by a sinusoidal wave. So for example, we have the pressure as a function of time is equal to the magnitude of the maximum pressure by cosine of omega t. So recall that omega for the harmonic oscillator being the angular frequency, was equal to 2 pi by the frequency in hertz. So we can write this as A by cosine 2 pi f by time. So in our case here, the frequency is 50 hertz. So the period is equal to the reciprocal of the frequency, which is 0.02 seconds. So as we can see, this is the time to complete one cycle of the oscillation. And in this case, we took the amplitude as 1 Pascal, and the sound pressure is typically represented as a sound pressure level in decibels, and there's a formula to convert to that. But for now, this pressure is representative of a sound pressure level of 94 decibels. So here our units of pressure are in pascals, and time is in seconds. Now alternatively, the pressure as a function of x is equal to the amplitude of pressure by cosine of 2 pi on the wavelength by the distance from the sound source. So as we can see, at x equals 0, or where x is a multiple of the wavelength, we have the maximum pressure. So we have an oscillation between compression and rarefaction, according to this cosine function. So when x is equal to the wavelength, which is this distance between those compression peaks, then we get cosine of 2 pi being 1. So for the wave to travel a distance equal to its wavelength, that's equal to the wave speed by the time taken for the wave to complete one full oscillation, which is the period. And recall the period is the reciprocal of the frequency, so that gives a relationship between the wavelength and the frequency being the speed of the wave through the medium on the frequency. So in our example here, the speed of sound is 343 meters per second in an air medium with a temperature of 20 degrees. And our frequency of the oscillation is 50 hertz. So we have 343 on 50 gives a wavelength of 6.86 meters. So our pressure here is in pascals, and the distance from the sound source is in meters. And I'll write down the sound pressure level formula, which converts the sound pressure to decibels for your reference. So the sound pressure level is equal to 10 by log base 10 of the pressure on the reference pressure squared. So the reference pressure is 2 by 10 to the minus 5 pascals, which is the lowest sound pressure that can be heard. And from that, you can substitute a sound pressure and obtain a sound pressure level in decibels, which is a typical scale used to represent the loudness of the sound.